Hello, and welcome back to part 3 of the chapter 5 on metabolism. We had just finished off talking about different kinds of enzymes. I gave you a whole bunch of different examples of them. They all have in common is they all end in ACE, and they tell you a little bit about the kind of reaction that they do. Like a polymerase, puts things together, and a hydrolase will take things apart. All right, so then we're going on to talk about the role of these enzymes in metabolism. What are they made of? Most of them are made of protein, and many of them are, in and of themselves, they're complete. There's just, the chain of amino acids, that thing is folded, it's got the particular shape, and then it's perfect, and it's done. But not all of them are like that. Sometimes you've got an enzyme that's partial. The term for this is an apoenzyme. It's not quite ready yet. It needs some other pieces to help out. And some of those pieces could be an inorganic ion. Things that we would ordinarily in our diets, we would refer to these as minerals, like magnesium or selenium. And then, so it could be an inorganic ion, or it could be another little coenzyme. And then when you put all of those things together and it's actually functional, holoenzyme is the term for it. I think it's a whole thing. So now it's whole. All right. The detail that I had skipped over before, I said enzymes are made of protein. Okay, most of the enzymes are protein. There are some enzymes that are actually made of RNA. So these RNA molecules are called ribozymes. And you actually knew this before I even told you this, because you know of ribosomes. Those are those little organelles that allow us to have the messenger RNA come in with the information, and then this ribosome with ribozymes as part of it, kind of move along that messenger RNA and do the translation to bring in the correct amino acid. So it's a kind of enzyme, ribozyme. Okay, here's a cartoon. Represented in blue is a protein. It's a long chain of amino acids. It's been folded a particular way, and it's part of the way to being a functional machine. But it's got these places where other stuff needs to fit first. We have, for example, a coenzyme. This is some other organic molecule that fits in here. And then there could be this inorganic cofactor, like I mentioned magnesium in passing. And then why are those pieces necessary? Because now it's fully formed, because this, for example, could be the active site. That is where the chemical reaction is going to happen that this enzyme is all about helping with. Some examples. I've mentioned the ions that can be a part, like magnesium. And then a whole lot of different coenzymes. You will not be surprised to learn that a lot of these are sourced from vitamins. Stuff that we need to have in our diets, but we don't need in huge quantities. And I keep talking about we, but this is true for microbes as well. So a bunch of the B vitamins, so B3, B2, B9, they all have names. Niacin is B3, folic acid, you know that one, B9. And so there's different versions of the molecule that's required for different chemical reactions. They have to fit inside these apoenzymes to make holoenzymes. Okay, what are all these holoenzymes for? Like, what is the whole point of that? Let me see if I can explain. Earlier, we looked at a diagram that looked like this. On the left, we had reactants. These are molecules that had a lot of potential energy, a lot of energy kind of stored up in the bonds. And then when they underwent a catabolic reaction that broke them apart, it released some energy. This was an exergonic an exergonic reaction, so there's energy that's going to be released. You start with the reactants, you end up with these products. Think complex carbohydrates to simple sugars. As that gets broken down, there's going to be energy released. Awesome. This does not happen spontaneously. So like in your pantry, if you've got some spaghetti, it doesn't like, oh my gosh, suddenly become a pile of sugar, right? You know, the reason that it doesn't become a pile of sugar is that this is a little bit inaccurate. It doesn't, this slide down here makes it look like it could happen at any moment, and that's not the case. There is, okay, so over here in this bigger diagram, it's representing the same thing. Do you see how the big red reactant bar is here? Picture that over here under this word reactant. So that's higher, and then the products are down here, so we're going to go downhill. But unlike the more simplified diagram, this is actually showing that you don't just go straight downhill. You have to come up over a hump. You have to invest some energy first before that reaction will go. And in the absence of an enzyme, these reactants we have to invest a lot of energy into this system to finally get this thing to fall apart and to start releasing some energy. Okay, this is known as the activation energy or the energy of activation. Think like, go back to that slide analogy. Like when we were thinking about when you were a kid and you were at the top of the slide, or I don't know, maybe you do this more recently. But you're at the top of the slide, there's this moment that you're just kind of sitting there and you're not moving yet, but you could, but you have to push off a little bit and then you go. Like that. This is the pushing off, and then it'll go. Okay, so reactions are going to need some investment before they'll go spontaneously. What an enzyme does for you is it makes it easier for you to get up over that hump. There's not as much of an initial investment that I need to make in order to get moving. That is why enzymes catalyze, they make the reactions go more easily. And what it looks like, again, if you have an enzyme, this could be an enzyme just completely whole. It doesn't need coenzymes. It doesn't need the inorganic factors. This is just, this thing's ready to go. It's going to have an area in it that's got a shape that kind of matches the reactants. We're going to call this substrate because that's what we call it when it fits into an enzyme. And so the substrate kind of matches the active site, but when they get together, there's more of a change. It's called an induced fit. And I know that sounds like a foreign idea, but you know exactly what I'm talking about. If you've ever shaken hands with somebody, you don't just like put your palm passively next to their palm. You actually wrap your hands around each other and you shake. Yeah. Okay. Like this. So they come near each other and then you get a closer grip, and then the reaction can happen. And here's a particular example. Here's fructose, and the substrate is fructose, and then this enzyme has an active site in it where the fructose can fit, and this enzyme is going to be one of those that breaks the molecule apart. So once the fructose fits in there, then the enzyme changes shape a little bit, applies some pressure, if you will, and that causes a break in some of these covalent bonds, which allows the products to be released. So they're smaller and they've released some energy. And so these pieces, go off to some other part of the metabolism, but this enzyme, importantly, the enzyme is unaffected. The enzyme is free to now go do another reaction with another fructose molecule. All right, so that is the end of part 3. I'll see you over in part 4.